Thank you very much for introducing me, Bowen. So, I'm having a blast. So, thank you very much for having me over for the session, and it's a real pleasure for me to be part of this, reopening, if you will, of this year's iteration of the GEMS seminar series. So let me just start my timer here as well, so that I don't lose track of time. Today, I would like to talk to you about going beyond the surface. So, and apparently, you can do a lot of things with halide perovskites nowadays. But so I promise you, this will not be a talk about speleology or submarine. Biology research. We're just looking into the interfaces in perovskite solar cells and how to analyze those interfaces by advanced XPS approaches. I'm speaking here to you from France, from Paris, or if you will, a little bit south of Paris. We're here at IPVF, located on the Paris-Saclay campus, not far from the airport Orly. So whenever you come pass by, maybe you do some measurements at synchrotron Soleil, feel free in order to get in touch with me. And now let's get to the topic. We are talking, when talking about halide perovskites, of course, about the next generation of photovoltaics, and which is really defined by hybrid materials and interfaces therein. So we have this departure from the classical crystalline silicon monojunction cell, and in order to go to multi-junction concepts that promise higher performance, so that you can actually get a higher yield per area, you need to build on thin film technologies and introduce those into tandem devices. And what we also know from our research, and I will present some evidence for this later on, is that long-term stability is really governed by tailored interfaces. So certainly there's been significant advances in the material itself, but interfaces are really the key point on which we have a knob on to improve that. Also mirrored in the surface passivation strategies that were just presented in by the speaker before me. Perovskites, and I have this slide here only for the sake of completeness, effectively, of this talk, makes a distinct class of light absorbers. Can very quickly glance over this. What is important is, of course, the tunable optoelectronic properties that also allows to tune the band gap and the energy levels. So these eventually would then also determine the energy level alignment, if it matters, as we will look into as well. But there are some caveats to this. The materials we observe high crystalline order in the materials, but they also feature dynamic disorder. They have low effective masses and low density of states at the band edges, which makes it particularly difficult to determine the band offsets, something that has plaguing us electron spectroscopists for the analysis of these materials. And then, of course, there are sharp optical absorption edges, low non-radiative recombination rates, except, of course, you manage to introduce some defects, though the materials can be defect tolerant and even show some sign of self-healing or better self-repair. Now, let's get back to the content of my talk. I've got 3 major chapters. Last one is actually very quick. We start off with the interface analysis for MHP, so metal halide perovskite semiconductors, starting off with the charge selective interlayers and the design thereof, analysis of buried interfaces by HAXPES, in order to then advance to the main body of work that is really to understand on what is the impact of interfaces on the optoelectronic and chemical properties when we construct a halide perovskite oxide transport layer interface, and how this is also buffered by organic layers that you can actually introduce. Eventually, this all comes with actually a requirement that you do your measurements carefully, as there are transient phenomena in photoemission studies going from degradation over beam damage to stimulate self-healing. So the question was, how do interfaces affect perovskite solar cell performance and stability? And how can we actually steer this and navigate this by the design of charge selective contacts? It's all driven really by the technology goals and approaches. We aim for high efficiency, reliability, and scalability. We want to integrate these devices into tandem cells, as I already foreshadowed. And then the interfacial design is then, of course, critical. As you see, there's this multitude of different interlayers and interfaces, and what is the best choice, for instance, here for the whole transport layer. nickel oxide, always nickel oxide, something else, self-assembled monolayers maybe. What are the requirements for the top contact, and how can you actually make a conformal top contact that acts as something that helps you to promote charge extraction from the perovskite, but at the same time also acts already as a pre-encapsulation layer that increases your stability. The approach that we go is this trifecta, of course, with a central pillar of interface analysis that comprises mostly photoemission spectroscopy work. We couple to photophysical experiments and then device characterization in order to close the loop and to begin to understand what are the implications of a specific interfacial alignment process on a device metric. And speaking of photoemissions, photoelectron spectroscopy, to be a bit more technical about it, this is the tool that has been established over the last decades for dedicated interface studies for semiconductor devices in general. You can roughly split it into ultraviolet photoemission spectroscopy if you use UV light in order to excite photoelectrons, XPS of X-ray induced photoemission spectroscopy when you use X-rays. And again, for the sake of completeness, also added IPS, so inverse photoemission spectroscopy, that allows you to look into the unoccupied states, whereas the other two are, of course, probing the valence band and also the core levels. In the schematic, what you have is you have, of course, the incoming photon beam that excites the electrons that are then emitted into vacuum, collected via the electron analyzer, set on trajectories corresponding to the kinetic energy that is coming from information about their binding energy in the solid, and then projected on the detector. So the entire measurement is dependent on the electron leaving the surface in an unperturbed state. And this is also where the limit of the application is. It's a very surface-sensitive technique. Nonetheless, we know that this surface analysis is still very strongly affected by the impact of the buried layers underneath. So for instance, if you start to construct your energy diagrams from this measurement and you measure just MHPs, so MAPI in short, on top of titanium oxide, you will find that at the top of the perovskite layer, the Fermi level is closely aligned to the conduction band, as the perovskite has been deposited on an N-type layer. If you deposit the perovskite on a P-type layer, for instance here, sol-gel nickel oxide, you find the Fermi level to be somewhere in a mid-gap position. So even though we are just sensitive to the first 2 to 5 nanometers, the impact of the layer underneath, buried 400, 500 nanometers below, still plays a significant role on the energy level alignment, as it seems. It is now very hard to assess this interface, but this is what the talk is about eventually. And now imagine that we start off with a standard vertical device architecture, and then the interface here is buried underneath all these layers, and you will not get to it. What we did then is we flipped the script effectively and conceived this lateral heterojunction device where we have an arrangement of coplanar deposited transport layers, a whole transport layer, for instance, nickel oxide, and electron transport layer with a gap in between. And the gap can be tens, hundreds of microns. And you then deposit the perovskite on top, and what you should then get is so either Fermi level pinning, so everything to be at the same level, or if you have a large depletion width, you can see at the surface the formation of the p-n junction between those two contacts. And that is exactly on what we're looking at. Something that we have started in our team with Sean Dunfield and Alexandra Bolia and Davide Regalo, which is now pursued and further deepened by Pilar Lopez Varo. And we see that starting off at the left-hand side, going to the right-hand side, or vice versa, we track the potential change of the surface, the surface change of the surface potential across this channel. We make out a region here above the nickel oxide that is set at 0, and then see effectively the built-in field between those two layers. Now, this is a little bit of a playground for us in order to test and to model that. And the initial model approaches were to simply take into account electronic effects. And then if you want to observe this change in surface potential, you can actually, but you need to go to very low doping concentration and also very low trap densities if you assume shallow traps, down to values that are below 10 to the 11 centimeter cube. So this would be quite astonishing, but it also doesn't take really into account ion migration effects or also the interfaces really. And where it all kind of stops to be that a completed picture is once you go to measurements that also involve the additional use of light. So going from Kelvin probe force microscopy measurements that you can also use in order to map out the surface potential to light-induced surface photovoltage measurements. And then you can make out a stark difference between the perovskite deposited on titanium oxide versus nickel oxide in the surface potential, a very strong jump that is actually not compatible with its completely intrinsic character of the perovskite or band offsets alone. So there need to be additional factors playing into this. You can also see that once you turn off the light, it does not return to its initial value. So that also tests that it's not a purely electronic effect. And indeed, once you look into this decay and compare it to what you get in a drift diffusion model, you are off in terms of first magnitude of the surface photovoltage, but then also in the decay time by here it's 3 orders of magnitude, or even 5 orders of magnitude in terms of the time. Actually, even more, 8. So with this, we also need to consider deep defects at the interface. In this case here with the titanium oxide layers, this is MHP on top of titanium oxide. That would lead to trap and release events, for instance, for this long decay. And indeed, there were additional indications that these defective interfaces play a role not just for performance, but also for stability. And I wanted to briefly home in on this issue in some earlier work that we published a while ago, where it was really key to enhance the perovskite stability, perovskite solar cell stability, even for an unencapsulated device by exchanging the interfaces. Here in that case, we started off with this triple cation mixed halide perovskite, spirometad as a whole transport layer and gold electrode. When you change the top, so you get away from the spiro to EH44, which is this molecule depicted here, and then also molybdenum oxide aluminum layer that mitigates metal and moisture migration into the perovskite. You enhance already an initial drop in power conversion efficiency over the first couple of minutes and hours, and then this was really key to it, substitute the bottom titanium oxide layer by tin oxide, you get to chemical stabilization against metal halide perovskite segregation. So it's something that we were very ready to observe qualitatively, but quantitatively, and pinning down exactly the process on what occurs at this interface that stops this segregation and degradation effectively has been an open question for a long time. And therein comes now how we need to hone our tools in order to get to these interfaces. So how do interfaces affect perovskite solar cell performance and stability? I ask again. And this time around, I'd like to present on how we get to this interface by HAXPES analysis. First, of course, some general points about HAXPES or photoemission spectroscopy. I talked about the surface sensitivity already a lot qualitatively, but quantitatively, the critical quantity is the inelastic mean free path. When you look into this view graph here, this is something that has been recorded in the 80s and 90s, is so-called universal curve of inelastic mean free path of electrons in matter. And it shows that with a factor of 2 or 3, you have more or less the same attenuation, independent, irrespective of the element that the electron needs to traverse. And you see a very distinct dependence on the electron energy. Of course, changing the photon energy in XPS then will also change the kinetic energy that the electron has in order to get to the surface. You can see that there is this minimum here at 50 eV kinetic energy, where the inelastic mean-free path is just merely 6 or 5 to 6 angstrom, something like this. Whereas as you go into the XPS regime, you increase the step. And then, and HAXPES not shown here, using new sources, for instance, chromium K alpha or gallium K alpha, going up to 9,251 EV, you enhance the mean-free path even further. The information depth you can approximate with about 3 lambda. You always need to consider this type of profile that you see here. So of course, you're always getting most of the signal from the surface, but you also get signal from deeper down in the subsurface region. I noted down just for general sense of orientation, some values of what you can expect for information depth for different photon energies when looking at the first core levels in the first several hundred EV binding energy range. And can you actually use this for halide perovskite research? Yes, you can. We actually did this on this example here for lead-free perovskites, formaldinium tin triiodide. In that particular case, what was known at the time is that, yes, you can put tin fluoride as an additive into your layer. It will make for better crystallization. There were some indications that it would aggregate at the interface, and we were able to show this also with top SINs. But what was actually even more astonishing is when you now perform your photoemission spectroscopy experiment. XPS with an aluminum K alpha source. So here you are restricted to about 5 to 10 nanometers, and then the gallium K alpha source going down. And it allowed us to show and see that
Excuse me, Philip. I think we lost your voice.
You lost my voice. Can you still hear me? Hello?
Yeah. You're now back. Maybe
Okay.
you can
All right.
repeat this part a little bit.
Okay, I will. Can you tell me where we lost it? So did you still get this slide?
Yeah, we have the slide, but
You have the slide. Okay, all
almost
right.
from the beginning.
All right, okay, let's go. So, XPS versus HAXPES of this particular interface system. What is not shown here on the slide is that P dot has a thiophene unit, whereas PSS sulfoxide, and these show in distinct sulfur core levels here, probed by HAXPES and also probed by XPS. What you can then see is once you add also tin fluoride, you get these additional peaks. And these new sulfur species actually correspond to tin sulfide at the interface. So this was something we did not expect, but once you introduce this tin fluoride, you inadvertently get tin sulfide, but only if you have a sulfur source in your substrate. And this also led us to the conclusion that it's actually critical to have this P.PSS in this lead-free perovskite device, which at the time you did not came across many studies that did not have working devices on P.PSS. And this was something we were able to see by HAXPES, in that case, inadvertently. Just very briefly, tin sulfide, of course, promotes hole extraction, but makes for a very poor mechanic contact, and you have to combat delamination and eventually then long-term stability losses. So let's see on how we can actually now also use HAXPES in order to identify the chemical origin and nature of defective interfaces when it comes to oxide perovskite interfaces, to understand on what is the driving factor for the for degradation, but also for these performance losses. So we tweak the experiment a little bit. We now not only look at the surface of the perovskite, but we actually put an overlay on top in order to look into band alignment and also this interfacial chemistry. In the past, we've exercised this for a host of different materials. This time around, I'd like to focus on the oxide layer by atomic layer deposition. And atomic layer deposition, not just because it can make beautiful oxide films that are ideally completely close and conformal, but also because in our production of technology, ALD plays a more and more significant role, be it also derivatives like spatial ALD. And there we know that ALD oxide films can be inhibitors of oxygen and moisture ingress. They stop ion diffusion, and if you do it right, they still function as good charge transfer layers. So we start off with this double cation multi-halide perovskite and run the ALD process on top. This means you pulse first your metal organic precursor, which in that case here is TDMA SN, so tetradimethylamine ammonium tin. You then purge with nitrogen. You then use your H2O2 for oxidizing the film, purge, and then rinse and repeat. You do this in order to get to a nominal thickness here, in that case of 5 nanometer on silicon reference. So given the fact that you would need to have the material also stick to the perovskite in the same fashion and manner. Something that is not necessarily given, but that we can calculate from our experiments. You then take the film and probe this by XPS and HAXPES, so soft and tender XPS, in order to measure the first 10 nanometers at 2 keV. And then the interface and buried layer probed by hard X-ray photoemission spectroscopy via HAXPES, going down to 25 nanometers in the subsurface region. We did all this for this and the next example that I will show at synchrotron and Bessie, together with a team of Markus Baer and Regan Wilkes, the beamline scientist Roberto from the Heike Endstation and KMC1 beamline at HZB. Now, looking at the different core levels, I'd like to walk you a little bit through how I want to present these things. You see here on the left-hand side the lead-4F core levels, and on the right-hand side the iodine 3D core levels. And blue is just the perovskite, and green is the perovskite with this nominally 5 nanometer thick tin oxide film on top. And what we already see is there is no formation of metallic lead, and as it seems no significant change to the peak shape and width. And this led us to believe, well, maybe there is not much to see in terms of defects after all. Also looking at 6 kV, we get to a very similar picture. But once you actually go into the quantification, you can identify depletion of iodine in the subsurface region. It starts off, it starts off with a stoichiometric ratio for the surface of the perovskite, and once you go to the subsurface, you see that they are slightly iodine deficient. But the real damage really is visible once you deposited the tin oxide on top, and then you see that your interface is highly iodine deficient. At 2 kV, we are closer to the interface. With 6 kV, we probe deeper into the perovskite, but still see a reduced iodine to lead ratio. This is also accompanied by different and more observations to be made, and that is on the nitrogen core level. In blue, here you see the nitrogen peak coming from meldinium. And it's still preserved once you go to the system where you have the tin oxide on top, but you also see the rise of an additional core level here, denoted as N star, that is more pronounced in the 2 kV compared to 6 kV, meaning that is mostly located at the interface. We went into libraries, literature to understand what can be the what does this P correspond to. Pyridinic nitrogen species made sense, and then once you take additional references or corollary measurements, so for instance FT measurements that we didn't do but others, we were able to see that and conclude that very likely we form triazine, which is a classical degradation product of meldinium containing perovskite, met this interface and really focused at the interface. And we also, of course, also tested the exposure of the surface to the ALD precursor, and were able to see this formation of what we suppose is simtriazine. So a lot of interface chemistry going on. Can we still assess the energy level alignment? One can at least try, and we do this by identifying peak shifts. Note that everything is always referenced to the Fermi level of the device. So by looking into peak shifts from 2 kV to 6 kV, we can see that the tin oxide is shifting, or elements in the tin oxide, but so also are the elements in the perovskite. except for the pure perovskite, not really. But once you go to the system with the tin oxide, you can clearly manifest these shifts. And what you then do in order to reconstruct your energy diagram is you assume the perovskite to be intrinsic. We've actually also measured this. Then you see your N-type thin oxide, and in between now you get some data points that would hint into upward band bending in the in the perovskite towards the interface, and downward band bending from the tin oxide. The question is this actually a valid approach, and eventually we refrained a little bit from this, as yes, this would be detrimental for electron extraction, but given that we have this significant chemical restructuring at the interface, we would refrain from making a solid statement about this. What we saw is that devices were not operational, and we were able to remedy this to some extent by introducing a thin PCBM buffer layer, but power conversion efficiencies were not very promising, and thus we did not further pursue this with the ultra-thin PCBM layer. But note that we still use tin oxide in our devices and modules here at IPVF if properly buffered. Now, is this universally true, or can we also find different oxide systems? So what about, for instance, the nickel oxide perovskite system, as we would now use or make use of it in an NiP structure when we deposit the nickel oxide on top? So this was a study that was performed by Nitin Malik, who was actually also the first author of the previous study, together with Javita Shemati, PhD students in my team is now postdoc at Synchrotron Soleil. Here, it's really the same thinking, same approach, but we exchanged the precursors. The nickel source, in our case here, is nickel bis alkylamidinate, whereas the oxidizer is H2O, so water, effectively. Again, we're aiming to get to a nominal film thickness of 5 nanometers. This time around, I'd actually like to spend a minute or two in going a bit deeper into the property of the oxide itself. I didn't show it before for the tin oxide, so you can take my word for it. Except for the slight changes in peak positions, the tin oxide showed up to be very stoichiometric, regardless if you measure it 2 keV or 6 keV. The situation is different for the nickel oxide. So yes, you get your metal oxide overlayer, but if you make the comparison here of the oxygen 1s core level from 2 keV to 6 keV, you can already see that it's not just the O2 minus moiety that you get, and that belongs to phase pure NiO, but you also see hydroxide groups arising, and of course some physics species that come out more clearly at 2 keV. And this goes hand in hand with the nickel 2p core level. It's actually not that easy to decompose. There is a procedure proposed by Mark Biesinger to have identify the different phases of nickel oxide, nickel hydroxide, and we see a much more significant amount once we go to the 6 keV measurement. That means the nickel oxide that is closer to the interface. So you can do this for the different photon energies, and then you make the ratios of nickel oxide, nickel oxyhydroxide, and even metallic nickel. And you can see, as you're getting more and more interface sensitive, these defective species here, ratio in this defective species rises. Now, what are the implications for the optoelectronic properties? Actually, we also find that this nickel oxide has a very low work function, which taken in itself and as an isolated value makes moderately sense, to be frank, but it's also an indication that whole extraction might not be ideal from this interface. However, what is happening on the halide perovskite side? So here we also see the emergence of this nitrogen defect species. This time we actually were not able to assign it readily to syntrizine, even though we tried with other chemical probes. And then going into the lead core level, there is no metallic lead, but we do see minor peak shifts to lower binding energies and broadening once we go from the perovskite to the perovskite nickel oxide system, meaning that yes, we very likely have also change in the lead halide core levels that are congruent with the chemical reaction, but it could also reflect on, this time around, smaller band bending at the interface. But this is, again, a statement that we cannot make with full clarity. as it comes to the iodine deficiency, it is there again. So we get iodine deficient interfaces, though the case is less aggravated than it was before for the tin oxide precursor. So here we actually make a very quick summary. So yes, we get these interfacial defects, but what is actually more telling is the gradation in the nickel oxide that is on top of the perovskite, and that should be really detrimental for hole extraction. And so then we actually buffer this in order to make the nickel oxide grow a bit more conformal and to our according to our wishes and our goals. And yes, using a thin PTAA layer, we found fewer defect species in nickel oxide, an increase in the work function, the lead core level reduced, broadening reduced, and also the iodine deficiency was not as stark as before. So this then made it into some prototypical devices, not a real HDL, just the thin PTA layer and ALD nickel oxide, no passivation whatsoever. But in this configuration, we still get some results and some working devices that go a bit beyond on what we had with the PCBM buffer tin oxide, for instance. And this was an important part. Does it actually aid to some extent to cell stability? And yes, even if this layer is very thin, you can see that if you had only this PTA layer, you see this initial drop, eerily similar to what we had for seen in the past on the spirometered gold surfaces, indicative of gold migration into the layer. And this is effectively inhibited once you have the ALD nickel oxide layer on top. Okay, so I close this part here by maybe quick mention of nickel oxide being problematic if defective. And yes, we know this from this paper from Caleb, where they also went with the hypothesis of nickel oxyhydroxide species probed by XPS, and were able to see the formation of lead diiodide if you don't process your perovskite with excess A-side cations and halides in order to make a film without this PBI2 formation. Now, this is how is this, however, linked to the chemical reaction at the nickel oxide interface? It's not entirely clear. So Javid Hashemati actually used these ALD nickel oxide films, and now we went the other way around. So we tried UV ozone treatment, but then we also applied these, very widespread used MeO2 pack surface modifiers that can make a self-assembled monolayers, but in any case make an organic interlayer between the oxide and the perovskite. Then actually took these surfaces and evaporated very thin layers, just 10 nanometer of MHPs on top. Was able to see in XPS that while you actually get for the, so I take just this gray curve here on top. If you have just nickel oxide, you can see here the nickel 2p core level indicative of nickel oxide with the hydroxide species. Once, and this is now the more noisy, more bold curve, you add the MHPs 10 nanometers on top, you see the rise of this additional contribution, which is metallic nickel. Now remember, this is also what we saw in the HAXPES measurements, the occurrence of metallic nickel. The UV ozone treatment doesn't stop it, but once you introduce the organic molecules, these contributions really go away, and you're now have an interface that does not have this chemical defect. Even though its optoelectronic activity seems to be different, it does not seem to lead to a lot of recombination, as photoluminescence actually does not change a lot, even if you have this metallic nickel compared to the other cases before with the tin precursors. Okay, so all nice and well. Were there any issues in taking these type of data? So yes, I said it initially, you need to be very careful about this. We had this long-running experiment here for an XPS measurement for 42 hours. This was almost 10 years ago now, of just MHPs. And then we could see clearly that the iodine to lead ratio was dropping off over time. We're losing methylammonium, we're losing iodine. So far, the valence band maximum seemed to be, or position of the valence band maximum did not seem to be affected by this a lot, very likely due to Fermi level thinning. And it speaks volumes to the care you need to take while doing this measurement. And in the past a couple of years, we were increasing our means or our understanding on how to treat these samples. So, for instance, comparing lab-based with synchrotron-based XPS can then also see the degradation. It's really that the dose makes the poison. So you need to go down to a low X-ray dose. You need to work with conformal samples, homogeneous samples, where you can evaluate multiple spots and average then afterwards in order to get to reliable data. You can, however, also couple this to very targeted degradation experiments. So here, again, just an XPS measurement of our triple cation mixed halide. You can, of course, then see in the spot change of the different core levels, a decrease in iodine and nitrogen. And indeed, when you do the photoluminescence imaging, you get a true metric of the optoelectronic changes induced in this iodine poor phase. And moving on now to this last example, we'll use formaldinium lead bromide. Here again, measured at the synchrotron with high intensity radiation. You can see on how the lead peak is actually growing as you're losing the more volatile formaldinium and bromine from the surface. You're forming metallic lead. But what was actually even a bit more intriguing is once we received the samples exposed for either 1 minute, 10 minutes or 60 minutes to the beam, you could actually see in a PL image the beam profile. So it's actually this small oval spot here that is the beam. You have a little bit of shadow that is an overshoot from the X-rays that are passing the different lenses effectively. And then you can see that as you increase the time, the X-ray time, and then take the image afterwards, can already make out a small change here in this region. And it even shows this strong recovery of photoluminescence for long X-ray exposure, which we found as stimulated self-healing. Now we could ask yourself, so how long will it actually go? Well, we could actually see that when you make your surface devoid of any formaldinium and bromine bromine is still there, but of any formaldinium by sputtering, for instance, you hold X-rays on it and you can see a re-emergence of the nitrogen peak as formaldinium is again reconstituting the surface. I conclude. So today we were talking about high efficiency, so the need for halide interfaces to implement perovskite solar cells. We have this lateral heterojunction platform that reveals the impact of charge transport layers, and that we use now at an experimental platform to check different interlayers. We were looking into interface defects and interlayer formation of this halide perovskite transport layer interface in perovskite solar cells. When you deposit ALD tin oxide on top, we find this trizine formation from formaldinium and decomposition of the metal halide perovskite into lead dihalide, which is then going hand in hand with some suggested band bending. Whereas in the case of ALD nickel oxide, yes, we also see these nitrogen defects and lead dihalide formation, but here this time we don't see strong recombination, but it's the defective hydroxide, nickel hydroxide layer that is detrimental for hole extraction, which we can, however, circumvent by buffering the system. And overall, this interface assessment, as I presented it, requires careful measurements, low irradiation flux. I'd like to thank the team, the collaborators, so Javid and Nitin, who really did the big part of this work, Pilar, Davide, and Alexandra, who have been working on these lateral structures. That still is a platform for us also to run operando measurements that we are constantly improving, and also the other team members that contributed also by the photoluminescence electrical characterization, somewhat older group picture I recognize given the age of my son. And again, all the co-workers from the different laboratories around the world, and you very much for your kind attention. Thank you.